Review of some of the things that we've studied and are going to show up on the test on Monday. I will answer any questions on the test or on the review before you take the test. So if you have any more questions, we can take some time on Monday to go through it before we start the test. A couple of things on the test. The test is going to focus on exponential functions and their inverses, logarithms. Now, exponential functions, you need to know about them and how to graph them. So we have our basic exponential function. Our exponential function in its most basic form is going to be a y equals ab to the x function. In this case, when there's not a d, a is the y-intercept or initial value. Those kind of mean the same thing. If there is a d here added on to the end of plus d like this, then a plus d is the y-intercept. Okay. B is known as my growth or decay factor. If x is positive, we'll say x is greater than 0, then it is growth for b greater than 1. And decay for b between 0 and 1. Remembering that when b is negative, we get imaginary numbers, and so that doesn't work for our continuous function. It can be a function, but it's not an exponential. If, however, x is less than 0, or x is a negative number, so there's a negative up here for the x. So if I have a negative in front of the x, actually, I shouldn't say this is x is less than 0. I should say if it is negative x. Because I don't want to refer to x values. I want to refer to x's. There's a negative in front of the x. The negative up here makes a reflection over the y-axis. And so this switches growth and decay. C is my horizontal shift, remember opposite sign, and D is my vertical shift. So if I have a function like, say this, I want to start by graphing just this function. This has a y-intercept of -3, and it's doubling. So as I get to 1, I go to -6, the asymptote being 0 if I have no translations from these two numbers. Now I will adjust for my translations. So I started with just my basic function with the y-intercept and my growth factor. Now I'll adjust for my translations. That's up 3 and left 4. So start with my up 3, and I'm going to move the asymptote up 3. Now I'll take the rest of these points and I will move them up 3 and left 4. I don't need to move an asymptote or a line left. Move that up 3, left 4, up 3, left 4, and this becomes my final graph. I can do these same transformations on logarithms. to so I will start with just graphing log base 2 of x. Log base 2 of x. Log base 2 of 1 is 0. Keeping in mind that this is the inverse of the exponential. So I have reflected the exponential 2 to the x over y equals x. Okay, so that's the 2 to the x in green here. Goes to this point 2, 1, it goes through 4, 2, 4. So that means my logarithm is going to go through 4, 2. So I really need to have 2 of these points. I should have a key 1 here. Log any base goes through 0. Okay, and then I should always have the point 2, 1. If it's base 4, that would be 4, 1. So now I can do my transformations. This shifts right 3, which is going to shift my whole asymptote right 3. My vertical asymptote this time, this is my horizontal. And then I shift each point right 3 up 5. So right 3 for this one comes to here, up 5 goes to there. My next point right 3 up 5 is up here. All right, 3, I got to go 2 more and more, and my graph ends up here. Okay, exponential functions become highly useful types of functions. We have our compound interest ones, where we have our initial amount, 1 plus the rate. Remember, rate must be a decimal, not a percent. Divided by the number of times we're compounding per year. So if that's quarterly, that's 4 times a year. To the, again, nt. Okay, this is an important formula. You probably want to make sure you get that to your notes. Or if we're doing it continuously, we use the special number e. Again, initial amount or principal for p, e to the rt. Okay. We can use this for anything, basically a very similar equation for any type of growth. Y0 is another way to write initial amount. Or y-intercept, it's y0 because it's y with an x-coordinate of 0. So if it's a growth rate, we do 1 plus r t. If it's a decay rate, we do 1 minus r t. And t is in whatever units we're talking about it growing in. If we're talking about it growing monthly or daily or annually, we could apply this if we need to. We have a yearly growth rate, but it's growing daily or something. You could apply that concept. But the key here is if we have a decay rate of 12%, we're going minus 0.12. I'm going to look over the test quickly and see if there's anything that I missed. Oh, a couple of things to note with these functions. You need to note intercepts, any x or y intercepts. You need to give domain. Domain on this graph. It doesn't include 3, so it's just 3 to infinity because it's an asymptote. It does not include 3, the x coordinates. The range, even though it appears to really level off, it can keep expanding forever. It just does very, very slowly. My end behavior. Normally with end behavior, I have to do positive and negative infinity. But in this case, the graph does not exist at negative infinity, so I do not need to include it. With the exponential, though, I would need to include the negative infinity and say it's going to 0. Okay. You may have to give intervals where it's increasing and decreasing. Now with a logarithm, it's either always increasing, or if we put a negative in front, it's always decreasing. Same is true with an exponential. Although exponentials could be decreasing in multiple ways. You should also know how to convert exponential to logarithmic form. Equals log base b y is x. We should know how to convert between these two forms, where the base goes to the base of the logarithm, the y on the opposite side goes inside the logarithm, and the exponent is what's equal to log. You need to be able to go both ways. And that's pretty much a summary of what's on the test.